Welcome back. In lecture 55, we will complete the last mile logistics, the second part of the lecture. So, the different concepts that we will cover will be on hyperlocal last mile logistics, then particularly hyperlocal food delivery in India, and then we will look into the distribution problem, how this could be used to solve this kind of last mile logistics issues, and then within distribution problem we will look into the traveling salesman problem, and we will solve it using an assignment method, which is also a very common method, the Hungarian method, and in that way you will also learn how to solve assignment problem as well. And then we will look into the vehicle routing problem, and finally we have got we will look into the different techniques to solve a vehicle routing problem, particularly these are all optimization techniques. And then we will solve a traveling salesman problem and a vehicle routing problem in the ArcGIS software using the network analyst extension for that particular software. So, when I say focus on hyperlocal, basically hyperlocal delivery is one of the last mile logistics model that is being increasingly adopted these days, and it's a delivery model where service providers acquires requested products on demand locally and deliver the same to the customers in the same area. So, that means certain delivery agents will based on the order a particular individual places, collect them from that retail stores in the area and then will deliver it to a person's house. This actually is very convenient for the individual, the person who is giving the order. The reason being he doesn't have to wait too much time and he immediately gets delivery. And it is also very beneficial for the logistics firm because it doesn't have to create a supply chain where there is a costly warehouse involved, and so that they will bring the warehouse from they will set up the warehouse in the city and they will take the delivery goods from the industries and then from there they will distribute. So, this kind of delivery is also not there. So, the benefits of this kind of system is it is less capital intensive and there is no investment required initially, and then firms tie up with existing retail and therefore they don't also have to maintain an inventory. So, they don't have to give orders, they don't have to maintain those inventory management systems. So, it also saves on office staff and back office work, and then mostly one-to-one delivery, therefore it is flexible. And that means in most cases what it happens, as soon as order is received, our agent is assigned to serve this order, and this order is picked up from one retail store and delivered to a particular individual. So, in most cases it is one to one, but of course we can always think about one to many as well, or from many to one as well. So, fast delivery is suited to time sensitive consumers. So, this is only possible if the customer is willing to pay that money for that delivery, and best suited for goods with a short shelf life like cooked food. Means if I do that for regular items, though there are several firms which have set up systems like that, but it is primarily good for cooked food where time is an issue. That means within a certain amount of time the delivery has to be completed. Now, what are the challenges? One of the biggest challenge in this kind of delivery is it's both origin and destination is within the city limits. So, these are subject to regulation, subject to all the laws, taxes and everything, and two-wheelers are preferred mode of use. So, as soon as it use of two-wheelers, so it is difficult to say is it passenger, will this particular trip generated a part of the passenger trip or part of the freight network, so or the freight travel demand. So, that is one issue, and two-wheelers are compared to is not that is compared to cars may not be polluting, but because there are so many two-wheelers that are used for one-to-one delivery, eventually the total emission is also significant. So, it is a highly competitive environment. Firms are reluctant to compromise on the level of service and are adopting faster and costlier delivery models. And so that means gradually this delivery services have become costlier, and it's always, you know, firms want to meet the time requirements and the time windows, and also gradually we cannot consolidate. That means it will remain as one-to-one delivery. So, that is one big issue that we need to take care of. So, sometimes during peak periods, ideal delivery partners generate a huge amount of parking demand. We see a lot of this these two-wheelers creating congestion in front of restaurants or in other retail stores maybe. So, that actually creates a nuisance in that particular area, and these models of delivery may be a burden on the already stressed urban infrastructure. So, these are the issues with hyperlocal delivery. So, it is very it's good business for the logistic companies, but if I take the urban perspective, or rather the perspective of the urban policymakers, then this sort of delivery actually is putting a lot of load on the system. So, now looking at hyperlocal food delivery in India, let us also look into the what happens in that particular system. So, online aggregators have created a software platform where consumers can place an order and from a local eatery, and usually the radius is something around 3 to 4 kilometers, and the ordering is dynamic. So, we cannot have no standard milk run delivery models. So, these are a group of models used to transport fixed loads from various suppliers to one customer. So, this kind of systems will not be effective like the ones we have already discussed last time when we solved the transportation problem and so on. So, deliveries are mostly one-to-one. So, this is one big issue. Once the order is placed, the platform matches the order to a delivery partner. So, once the order is placed, a delivery partner is linked with that order, and he is supposed to deliver that order to this individual's house. So, what is the terms of engagement between aggregators and the delivery partners? The partner receives a payment based on commission and incentive structure. This commission per day depends on number of deliveries, total kilometers travel, and the waiting time spent, and the partner bears the cost of delivery vehicle and fuel, which is significant, and sometimes people will not add the capital cost of that particular vehicle. So, if we take into account both the capital cost of the vehicle plus his engagement cost plus the fuel, then probably the payment amount may be significant, may not be that significant. And a minimum wage is guaranteed per day in lieu of the delivery partner logging in for a fixed minimum number of hours, and additional daily, weekly and monthly incentives are also given. So, this is more or less the hyperlocal delivery that is going on in the India right now. And once this delivery agents accept the order request, he moves to the location of that particular eatery, and this distance is called the first mile, and this is a paid mile. That means he gets paid for this kilometers traveled, and then once the order is picked, he delivers it to the customer address, and this distance is called the last mile, because same as the last mile delivery, and this he is also paid for that. And he also after the order delivery, the partner locates himself or herself using a heat map, that these are the areas where likely orders are going to come up, or right now there are a lot of orders, and like same as this ride sharing as well. So, that is he has to go towards that particular area, but he is not paid for this particular part of the journey. So, this kilometers is not added, and this is called a dead mile. So, this is the way delivery agent starts. He does the first mile, he goes to the eatery, waits there for some time. So, this is waiting time he gets paid for. Then he travels again, and then this is the last mile where he delivers. For that he also gets paid, and then there is a dead mile where he is not paid. So, depending on how do we optimize this kind of systems, this there has to be strategies that has to be designed to reduce this dead mile component. Otherwise, a person will not make money for this dead mile. So, if he waits at this particular location, then he doesn't spend any fuel and all, but when he gets the order, he will be paid for that particular money. So, but his chances of getting an order at this customer's location is also very less. So, this is where he has to compromise, and certain algorithms comes into play, how to locate him so that he will go to a point from where he is both likely to get an order as well as his overall travel distance is minimized. So, this is the way hyperlocal delivery occurs in India, but to understand this kind of systems, we in the last lecture we have discussed about how to determine the freight flows between supply and a delivery point, and then how to determine on the location of a transshipment center, how to determine the distances. So all these things we have optimized using the transportation problem and the transshipment problem. And then over here, the idea is to understand what sort of trip or a tour a person has to undertake so that he does his deliveries efficiently. So in a context of hyperlocal food delivery, it is basically one-to-one delivery, but there could be other systems, or we can also make sure that a person, when he delivers, if he can consolidate some amount, like for example, he takes the order from 3 persons from that particular restaurant based on the time window of the order, and then he delivers each one of them one after another, and then he returns back. So how to optimize this for the entire number of delivery agents who is working under that particular area. So this kind of systems needs us to look into some other kind of solutions, which is primarily known as the distribution problem. So when we are setting up, when we are trying to determine the freight flows in an urban area, one is to determine the freight, what kind of distribution system will be adopted, and then what are the likely routes taken up by vehicles for different kinds of deliveries. So similarly for the last mile deliveries and for the hyperlocal deliveries, and so we can also not even hyperlocal, but even for restocking tours where a vehicle, like a vehicle coming out of a bottling plant, is going to, for soft drinks, is going to different stores and delivering their goods and then returning back. So this kind of systems, the routes they will adopt, or the way the tour would happen, is actually determined through this distribution problem. So distribution problem, where provision of goods or services from a depot, like a company, or it could be a retail store, to customers, is actually taken care of. So the problem can be modeled using graph theory through 2 ways. One is, not 2 ways, there are 2 variants of course. One is the traveling salesman problem and the other is the vehicle routing problem. Now a traveling salesman problem is basically a single route node service combination problem. So that means a particular vehicle starts from a depot and then it serves the different nodes and then again comes back to that particular depot, or it could also end up in another depot, provided their supply and the delivery points are different. Like for example, in case of waste management, you are starting from a depot, but you go and deliver the goods to a particular location and then again come back to the depot, or you may stay back over there. So we can say that eventually if he goes back to that particular delivery points, from there the next point definitely would be the first depot. So more or less it is the same thing. So traveling salesman problem determines that there is determines the route a vehicle will undertake, so that it reaches all the nodes, and then it doesn't revisits another node again, and it creates one tour covering all the nodes. So here there is no vehicle capacity limitation. So as I was saying that we could do it with solid waste management, but solid waste vehicles also do have vehicle capacities. So a vehicle, when it gets filled, it cannot be able to pick up garbage from other places. Or suppose a person is delivering food, so he has got a particular capacity. So only that amount of food he can carry and deliver. So that is one limitation that the traveling salesman problem has got. And it's find the minimum traveling distance and the cost for visiting fixed locations, and it connects any 2 nodes with the shortest path. So if I know the shortest path between each of these nodes, so I have to find the combination of in which order I can visit these places. So you can understand for suppose 3 nodes, 1, 2, 3, if I start from another depot, so suppose this is one depot, I go to one node, another node, and this way. So this is one route combination. So I could have also gone like this, this, and this. So in this way I can create many combinations. So as you can understand, when the total number of combinations increase, then automatically it's very difficult to compute or determine how many mathematically that how to solve this kind of problems, because it will be exponentially a huge number of solutions that needs to be looked into. So this is the traveling salesman problem, and these problems, that's why NP-hard optimization problems. And the challenge is when the number of nodes increases, the computation time increases significantly. So, in vehicle routing problem, it's a variant of the traveling salesman problem where we introduce vehicle capacity. That means a vehicle cannot be used to serve all the nodes if its capacity gets filled. So, there are two ways to solve that. Either we can use multiple vehicles to solve this particular problem. That means each vehicle will go to a set of points which actually is based upon its own capacity, or we can decide different time windows. That means this vehicle, same vehicle will be used in different time periods to go and serve different points. So, a vehicle routing problem is a route optimization method where multiple route node service combination problem is solved. Vehicle capacity limitation is there, and it is equivalent to multiple traveling salesman problem where all salesmen have the same starting location. So, we start from the depot, we have got different salesmen who go to different points and then return. So, the combination of all these tours made by each salesman should be the one with having the least cost. So, that is what we are trying to find. So, first we will solve the traveling salesman problem using the Hungarian method, and this is an assignment problem. It is a subset of the transportation problem, and the objective is to assign number of resources to an equal number of activities so as to minimize total cost or maximize benefit of the allocation. So, this is Hungarian method could be used for solving traveling salesman problem, but similarly there are other methods to solve the traveling salesman problem as well. But because Hungarian method is basically an assignment problem, so I am solving that so that you can use it for some other problems as well. So, you can understand that the objective is to assign a number of resources to an equal number of activities, and that means we have to do matching between the starting point and the delivery points, and to determine which combination are the shortest one. So, which overall when we add up all the cost, which would be the minimum cost, and if I can connect them in sequence and they follow the principles of this TSP problem, then it could be also used to solve a traveling salesman problem. So, a traveling salesman problem has to visit n cities, and the tour should end in the city where it started. Each city has to be visited exactly once. So, if my allocation problem, if I can connect the different allocations one after another, assuming that it is not from different supply points, we are supplying to different delivery points, but it's assuming that one vehicle is going from one point to the next and from that point to the next, and if this allocation could be following this TSP where the tour should end in the city and it satisfies this condition, then we can use this for allocation. It's this allocation problem for finding the TSP as well, the shortest route as well. So, we will explain that when I explain using an example. So, the objective is to select a sequence in which cities are visited in such a way that its traveling time is minimized. So, what are the different steps that we do? First, we generate the OD matrix of the cities, that means the distance between the cities, or we can say any kind of cost, that it could be distance, it could be time, any kind of impedance. Then the first step is row minimization. What we do here? We subtract the minimum value in the row from all elements in the row. Then we do column minimization. So, again we subtract the minimum value in the column from all elements in the column. So, these are the first two steps. After the first two steps is done, in the next step we have to do something called row scanning. What we do? If a row has only one zero, not 2 0 or 3 0, if it has got 2 0, we ignore that. If it has got 3 0, we ignore that. But if a row has only 1 0, we mark it. Mark it means we can put a box around that particular 0, or we can just anyway mark it and draw a vertical line through it. So, if it's a row, so in a table, so if I find there is a 0, so I will draw a vertical line through it. And if a column has got only 1 0, we will again mark it and draw a horizontal line through it. So, these are the first 4 steps. Then what we do is, the total number, then we check that if the total number of marked zeros is same as the order of the matrix. So, if it is a 4 by 4 matrix or a 5 by 5 matrix, the total number of zeros that we have marked is same as that. If it is same, then we have got a solution and we will go to step 9 where we start the route assignment, or we check if this particular assignment matches the TSP criteria. So we will go into step 9, but if it doesn't, so then what we do is we select the least value among the values not covered by the vertical and horizontal line. So in a table, as I have told you, like suppose this, suppose there is one vertical line, horizontal line, then there are two, this vertical line. So we will choose the cells which are not having any kind of line on it, and then we select the least value among the values not covered. So we will select the least value of that, and we subtract the value from all other values not covered by the vertical or horizontal lines. So that means we find the least value and subtract it from all the other values, and the value should also be added to all the values lying at the intersection of the horizontal and vertical lines. So we will also add that particular value to this particular location. So once we have done that, then we have to again repeat from step 4. That means we have to do row scanning and column scanning. And once row scanning and column scanning is done, again we have to check if all the zeros are should be of same as the order of the matrix, then it's fine. If it's not, we again repeat this entire process. Then once we have checked that the total number of marked zeros are equal with the order of the matrix, we say that it is all fine. Then we start the route assignment problem, and we start route assignment based on the marked zeros. So suppose there is a 0 over here, it is marked. So this is A, this is B, this is C, then this is A, B, C. So A to C is 0. That means A can go to C directly at the first. So at the first step. So that is called route assignment. So if a route fails to, once we do that, so after that we go to C, from C to, suppose there is a 0 over here, so C to B. So A to C, then C to B. Then we check B and see where there is a 0 over in this particular cell. Suppose 0 is over here. So B goes to C. So that means it is not completing. So we go from A to C, C to B, and then it goes to C. It should have gone to A. So that is a mistake, right? So that it doesn't satisfy the TSP criteria. So then if it doesn't satisfy the TSP criteria, we have to make another assignment. How do we do that? The assignment start with the next 0, and if no 0 is present, the next highest value. So if there is no 0, if there is another 0 in that particular row, then we will choose that. If it doesn't have any further 0, then we will choose the next lowest value. And then we have to repeat the row and column scanning method. So in that particular method, once we do that, instead of just looking at zeros and putting a line, we have to also look at the 0 and that particular least value that we have just selected and start putting lines on that as well. So that is how we solve the traveling salesman using Hungarian method, and this is called the inspection method of assignment. And we could have also used the branch and bound method, which you can also study. So let's see an example. So this is the matrix. We have got A, B, C, D, E, these 5 points, and then these are the impedances that are given. See the diagonals, we have given the symbol M. We could have also given a symbol of infinity, just to say that we will not touch the diagonals, because nobody is going from A to A or B to B and so on. So A to B is 4, A to C is 10, which basically means these are the impedances, either travel time or travel cost, from A to B or A to C, or from any point to any point. So in the first row, we will do that, identify that 2 is the least value. So we will subtract 2 from all the rows, from this particular row. So when we do that, we arrive at 4 becomes 2, 10 becomes 8, 12, and so on. Similarly, once we have done it for all the rows, we get this particular matrix. So you see, we have got a 0 over here, 0 over here, 0 over here, 0 over here. So now we do once our row scanning is done, then row reduction is done, then we look into the column reduction part, and then over here we go from this column. So there is a 0, so we can subtract 0 from these values. So it has got no effect, it will remain same. We can subtract 0 again, no problem. Then over here, then we see in this particular row there is 2 over here, and these are the least values, there is no 0. So that means we have to subtract 2 from all the values. So that's why we have got 8 becomes 6, 2 becomes 0, 4 becomes 2, and 2 becomes again 0. And then again we have got this, in this particular column there is again another 0. So, we have no, there is no, after subtraction it remains same. Same happens in the last column as well. So, once we have done this row reduction and column reduction, we have to do row scanning and column scanning. So, what we do is we select the first row, we see that there is a, since here we have got a 0, so there is only one 0, so we mark it. So, that is why we have given a yellow, deep yellow color, and so we will have a vertical line through it. So, that means this row is not looked into. Then we come into the next row, we see there is a 0 over here. So, we put another vertical line. Then we come to this, the third row, there we see a 0. So, we put another vertical line. Then over here we see another 0, we put another line, and same over here. So, we see that all the rows are marked. So, column scanning is not required. But if there were some rows which were not marked, some not all of them would have zeros, then after our row scanning we would have done column scanning in the same way, and we would have put again so after in the column scanning we will have put horizontal lines. So, now we check total number of marked zeros is equal to the order of matrix. So, we see that 1, 2, 3, 4, 5. We have 5 marked zeros over here, 1, 2, 3, 4 and 5. So, yes, this is same. So, we can go to assignment step, which is we will discuss in the next slide. So, if it is not, then we select the least value among the values not covered by the vertical or horizontal lines. Subtract the value from all other values not covered by the vertical and horizontal lines. Then this value should be added to all the values lying at the intersection of the horizontal vertical lines, and then we have to do row and column scanning again. So, this because we are lucky, we ended up with in the first step our order of matrix matches, but if it had not matched, we would have to do all these steps. So, in the next step we start doing the assignment. So, this is my the matrix from the last slide, and we see that we go to the first point A, and over here we see that at the first row we select the 0 marked at AE, like over here we have a marked 0. So, we select that. So, this is our first root. And we say that all zeros, and once we do that, we have to do another row scanning where we have to also mark these zeros as row and column scanning, where you have to mark both mark the zeros. So, instead of saying that, we can also say all rows in the row and column of AE are cancelled. So, that means because we have selected over here all the zeros in that row we have marked with red, and all the, if there were zeros in the particular row, we would also have marked in red. So, we have marked the zeros in that particular column as red. So, that means the first root is AE. So, now because we have reached AE, let us go to E and see where we are going to. So, E, here the mark 0 is at A. So, that means from E we are going to A. So, the root is AEA, which is not possible, and because it does not satisfy the TSP criteria. So, we will say this is not a proper assignment. So, we have to restart this particular procedure. So, in the next step what we do is we select the next least element, which is in the first row. 0 is done. So, these are marked. So, we have taken 2. So, once we have taken 2, then what we have to do? We have to mark both zeros and 2 in this particular row and this particular column, and then we say that those we have to cancel. So, that is why we have put this as red and this as also red. So, 2 is selected. So, we have selected the first root as A to B. Now, then we go to B. In B we see the value is at C. So, we mark C, and then again we cancel 0 over here, and there is no 2, and then we along the column there is 2 and 0. So, we cancel both of them. That is why we have made them red, and these two are already cancelled, and then we move. So, the next from B to C is the next root. So, A, B and C. So, after C we go to C and we see the value, the marked 0 is at D. So, over here this is as we have selected, and but along this column and row there is neither any 0 nor any 2. So, there is nothing to mark, and finally, we come to a point where in the from D we see that the next value is at over here 2. So, this is the least value. We have already selected 2 as the least value. So, we select D to E, and when we do that we have to cancel everything on that particular column as well as on that row. So, all this got cancelled, and in the final step from E we can also go to A. So, now we see that the route actually is in sequence A to B to C to D to E and then to again A. So, this satisfies the traveling salesman problem, and we can use this as one of our assignments, and this is the TSP solution that we were trying to find. So, this is how we can solve for TSP. Now, coming to the vehicle routing problem, this problem was first defined by Danzig and Ramsar in 1959, and they were trying to dispatch vehicles from a bulk gasoline terminal to the different service stations, and that is when they came out with this problem. And the solution required a number of optimal routes for each vehicle, starting and ending at the bulk terminal and covering between them all the different service stations. So, this addition of more and more, so this was the basic starting point of the problem. So, there was a capacity constraint because the vehicles had got a capacity constraint, and that means they are also they require more vehicles. So, there has to be multiple routes. So, these are the new things that came in this particular problem, and gradually over time more constraints were added, and that resulted in various sub problems of the vehicle routing problem. So, some of the popular sub problems. So, one is the capacitated VRP. Here all the demand points have to be served, and the total quantity assigned to each route should not exceed the capacity of the vehicle. So, this is the first constraint that has been added. Next, the constraint is multiple depot VRP, where customers have to be served from several depots whose locations are intermingled with them. That means, instead of one depot, there could be multiple depots. So, then there is periodic VRP. So, over here we take a period which is suppose m days, and the vehicle may return to the depot at the end of that particular period and not at the end of a particular day, and the customer may be visited multiple times, t times in this m day period. So, this is a periodic VRP. And then there is a split delivery VRP, where a customer can be served by multiple vehicles if the demand of an individual customer exceeds the capacity of single vehicle. So, that is also possible. So, this is another relaxation to the VRP problem. Then we had stochastic VRP problem, where some of the components like customer demand or the number of customers or the times, this could be a stochastic, we can assign probabilities to them. So, if we assign if there is stochasticity, so this kind of problems can take care of that. Then there is VRP with pickup and deliveries, which is also known as backhauls. That means a customer can return goods besides taking delivery. An assumption is made that the returns are acceptable only when deliveries are complete. And finally, we have got VRP with time windows, where customers have to be served within chosen time windows. So, you can understand that these problems are very, very complex, and that means there could be millions and millions of solutions, and the number of solutions increases exponentially with the addition of more number of locations that has to be served, and more number of options that are put in, more number of constraints are put in. So, this cannot be solved using normal techniques. So, if we so this is the optimization problem, and there are of course exact techniques. That means we will look into all the feasible solutions and find the least cost one, and then there are heuristics methods. That means we will adopt certain techniques to reduce the computation time. Now, how do we do that? When we do exact techniques, this exact techniques guarantees the optimal solution. So, that means we will find the least cost solution, and time taken may increase exponentially with problem dimensions. For NP hard problems, it is a nonlinear programming, these are hard problems. For example, branch and bound algorithm can look into all the different options and then give us the solution, but at the same time it takes a lot of time. Whereas a heuristic method, they do not guarantee optimal solution, they guarantee a suboptimal solution which is near to optimal, but the techniques may be but they reduce the total computation time by a huge margin because they adopt some strategies. So, techniques may be a problem specific and given solution in reasonable time for NP hard problems. So, that means they will find some trend in the way the solutions are coming, and then they can skip to another zone and start checking, or they can do locally in one area, they search the solution. If they do not find, they skip and then go and search for another solution in another area, and so on. So, or they use some other kind of rules and procedures which are also used to come out with the final solutions. So, some of the classical heuristic techniques that are used, these are a normal exact algorithms do not guarantee optimal solutions in reasonable times when the number of demand points are large, typically more than 100. So, some classical algorithms are Clark and Wright's, which is also known as the savings algorithm. This is a very popular algorithm for solving this kind of problem. And then there is a two-phase algorithm. Then the two-phase is a broad term. There are a lot of variants for this kind of algorithm. What it actually does is it decomposes the problem into two components. First is clusters these demand points into near points are first made into clusters. Then once the clustering of demand points is done, then feasible routes are determined for this cluster, because you are clustering many points, so your number of feasible options reduce. And then once the least cost path among the clusters is done, then another sub optimization is done within that cluster to deliver within that particular cluster. So, this kind of problems could be solved using this two-step process. So, that's why they are called two-phase algorithms. And then there is local search method, where local search moves about the solution space from one neighborhood to another in search of optimum solution. So, now we have heuristics, classical heuristics techniques, and then there are meta heuristics techniques. Now, in meta heuristic techniques, the techniques itself can form new heuristics or can form certain rules which would be able to determine during the runtime of the solution. So, in this a heuristic technique may sometimes gets bogged down in the local area, and it can misinterpret a local optimum as a global optimum, whereas meta heuristic techniques, what happens, they can drive the search from local optimum to global optimum. What it means is, even though it finds a good solution locally, it will again search for solution in other places following certain rules and procedures, so that overall the total cost becomes less. Overall, they find a more global solution out of all these smaller locals. So, this kind of techniques are actually a little bit more advanced than the heuristic techniques. So, some of these popular techniques that are used are called simulated annealing. In a normal search, a new move is not accepted if it degrades the solution. That means, if a normal heuristic, if I go on searching, if I say that the next option is not good, then I will not go in that direction altogether. But simulated annealing, it accepts a degrading move with a probability, because some of this, maybe the next move is degrading, but after that it may actually take a turn altogether. So, in a better direction. So, to avoid this kind of bogging down at the local level solution, because you are ignoring those alternatives. So, this kind of simulated annealing can actually go around that particular problem. Then there is taboo search, where this taboo search accepts a degrading move in the absence of an improved solution, and a taboo list of recent moves is maintained to avoid cycles, and the taboo list has a taboo tenure and a duration, that is the duration for which a move remains a taboo. That means, it remembers that these are the moves if that were taken that creates a bad result, and it keeps that in mind, and once that time is over, then it can again go in that particular directions. So, in that way it can again avoid the local minimum. So, adaptive memory search, in AMP, a list of good solution is maintained and updated throughout the search. Periodically, some elements or clusters from the list are extracted and combined to produce new good solutions. And then we have got two optimization techniques. One is ant colony optimization and genetic algorithms, which follow certain things that we see in nature, certain strategies that are seen in nature, like in ant colony optimization, the way ants move, the pheromones they leave, that leads to more ants going through paths. So, certain paths are more traveled. So, this kind of strategies are adopted. So, in VRP, a multiple ant colony optimization is utilized, where one is for minimizing the total number of vehicle routes, and the other for minimizing each route length. So, these are the two ant colony optimizations used within this ant colony optimization technique for VRP. And in genetic algorithm, it uses the biological principle of evolution to find better solution. In each VRP, each chromosome is a string of vehicles and customers served by it, and the fitness function for each chromosome is a quantity determines the quality of the solution, And in this particular VRP's case, the quality of the solution is the route length. So, better the route length, better is the solution. So, these are very broad ways to define this kind of techniques, but we cannot cover all this in this particular lecture. Just to let you know that these are the different options available, and you have to do a lot of coding to incorporate this kind of techniques to solve a optimization problem. So, alternative option is also there. That means, we can also solve this TSP and VRP problem using our ArcGIS software. We have discussed ArcGIS. You can download that free of cost for a limited period to test all this. But this extension that we are using, network analysis, that is not available. You have to buy that. So, I am showing that. So, in case you get the opportunity to use this network analysis, you will be able to solve TSPs and VRPs very, very easily. So, in ArcGIS, you have seen that we have developed different layers or shape files where we have done the different road networks and so on. So, but when we do network analysis, we have to convert these road network shape files into link node diagrams. So, this is the starting point, and as you can see in ArcGIS, we can do analysis of routes, we can do closest facility analysis, we can do service area coverage analysis, we can do vehicle routing problems and so on. And the first thing that we have to do in this particular, when we solve TSP and VRP in ArcGIS, is to add a network layer, or rather to make the network layer, convert my map into a network with links and nodes. Then we have to set up the properties of the vehicle routing problem. We have to give parameters to define what kind of vehicle routing we want to do. Is it a sort of simple vehicle routing like a TSP, or is it having lot of constraints like time windows and all? So, that we have to set up. Then we have to create this vehicle routing analysis layer. Whatever results come out of this, that has to be stored in a layer. So, that also needs to be created, and then we have to run the process to get solutions. So, this is the broad steps. I will just touch upon some of the steps and take you through the process. So, we have to start ArcGIS, then in the catalog window on the standard toolbar, we can click on that. Then we select the location of the road network dataset or shapefile for which we want to develop this. We can then select new network dataset, and we can also include the impedances of that network. For each link and node, we can include impedances which could be travel time, travel cost and so on. If required, we can add some new attribute, because the shapefile may not have all attributes that we require to solve a VRP or a TSP now. So, we can add those particular attributes, and we can add the travel mode for the network analysis, and we can create and build the network dataset finally, and we get the link node diagram once the network dataset is built. So, this is a map of IIT KGP campus. So, we have done this shapefile, and then we start modifying this. So, we go to catalog, we then start the new network dataset, and once we do that, from there we can actually open up our shapefile, and these are the different parameters. You see, we have got the length of the road, the speed along the road, the total travel time in minutes, and then restrictions if it is two-way, one-way and so on. So, all these different things we have listed there, and we can also list the travel times for different modes as well. So, that we can do, and then what we can do is we can also add certain if these data were not there, we could have also added impedances, all these values as well for each of these particular links and all. So, once we have done that, then we have to create this new network data set, and here we can add those if we want to add some new attributes, like over here we have added the cost is in minutes and meters also is cost. So, these are the two cost items that we have introduced, because we are developing a network, we have to give the impedances, and then we have to add the restrictions. So, we can see over here, like for truck type is automobile, impedance is in minutes, distance is in meters, and U-turns are allowed. So, this we have done, and then we say create the network data set, and after that we can get after this process is over here, as you can see, the process takes some time to complete, and then we have our link and node diagram which shows like this. So, we see there are nodes and each has been converted into links. So once we have done that, we have to set up the vehicle routing problem. We click on this network analyst extension. You may have it in your ArcGIS installation if you have that already. So you can click the network analyst in this option, and then you get this particular screen where you can actually select the option what kind of analysis you want to do. So over here, this is the network analysis window. You can see we can set the depots, we can set the routes, we can have one route for TSP, we can have multiple routes for VRP, and then we can also use that we can set the different restrictions for those routes. Like over here, we can set the properties like capacity count is 2, that means it could be either in volume or in weight, and U-turns at junctions are allowed or not, that we can set. Travel time is in minutes, distance is in meters, and we can set this all for this different particular analysis. And so on the network analysis window, click on analysis setting tabs. In analysis of layer properties, set the time attributes to minute and distance to meters, set the default date, set the capacity count. 2 means capacities were measured in 2 measurements, for instance volume and weight. So capacities of vehicles are set. We can give both volume as well as weight, and time field is in measurement is in minutes and meters. U-turns are allowed, and then we can set it to be OK. So once we have done that, we can see now we have to select that which are the loading points or the delivery points. So that means we have to also add the for traveling salesman problem, we have to first add the load locations. So using this option, we can add the load over here, and once we do that, then we can start a new vehicle routing problem, and in the load location we can take it from a particular file which is already there in a shape file. That means these are the load locations which are being shown. Then we have to also select the depot. So like over here, the options you can see, click network analyst on the network analyst toolbar, click new vehicle routing problem. The analysis layer is added to the table of contents window. Like over here, last time I showed you that initially network analysis classes are empty. Right click orders. First we have to set the orders and choose load locations. So order points are the locations that we have to visit. So those has to be loaded either from file, or we can also add them. Select location file, set the appropriate fields in the location analysis properties, and then we have to load the depot, that which point is the depot, and choose again from load locations which point is the depot, and select locations file, set the appropriate fields in the location analysis properties, right clicks on routes and add items. So for each route we can also set up that value, and if the properties window for a route specify attributes for the route such as time window, cost per unit time, vehicle capacities, this we can set up for that particular route, and then we can select the delivery locations, and then we can run the solver. So solver is basically this new vehicle routing problem. Within that we are going to set up all this. So here we can see that route assignment is done. So this is the solver which you can click, and this is the solution that comes in. It tells us from where the vehicle will go to where. So for this route 1, these are the different properties of that route you can set. This says the earliest start time and the latest start time, and then these are the maximum order count. This is also you can set cost per unit time. This is set as 1. So these are the things you can set for this particular route assignment, and then when we run the solver, you get this kind of a solution where you can see the this is the delivery location. This we have got 2 depots sort of. From here the vehicle will again come back over here, and these are the order points. These are the different order points, and this is the depot location. This is from where the vehicle will start. It is yellow, but this shows as black because it is selected. So when the route, this shows us actually the route, how the vehicle has traveled to different points using this particular network, and this we can also get the data from over here, that what is the total cost per unit time for this. Total cost comes as this, and the start time is around 9 o'clock, end time is around 9:46. So within 46 minutes we would be able to go and go to all the points, and then also go to a final depot. This could be from here again we can come back, so that will add another time as well. So this is what we have solved. We have solved it with 2 depots. Start and end depots are different, but we could have also solved it with the same depot as well. So this is the TSP solution. We do the same thing for VRP as well. Only thing is, in VRP, we right click on orders and choose load locations. Order locations first has to be done. Then the same thing we have to do for depot as we have done earlier. Say, then we go for this routes, and we can add another route. So last time it was only one route, we can now add two routes. And in the properties window for the route, we can give the attributes such as cost, per unit time, capacities and all like the last time, and select two different time windows for two different routes, or we can also have the same time window. Both of them would be happening at the same time, and then we can also select the delivery locations which are the same area that we are serving. And so we have got this two results that are coming in. So this we have set for pickups. These are the pickups. Deliveries we have not given anything, and these are the service times. That means how much time it would take to serve each of these particular locations. That we also can add. And once we can add that, then this is the solution that is coming in for each of this route. We set the properties. Like for two separate routes, we have got two start times. One is at 9 o'clock, one is 12 o'clock. If we do this, that means the vehicle, once it ends, it can again go and start the next area. Zone by zone, it can also cover the different areas. Or then we can also set the cost as well as the maximum order capacities and so on. So this is the final solution, where green shows vehicle the route taken by one vehicle, and yellow shows the route taken by another vehicle. And that we have got solutions for two routes, and one route take around 43 starts around 9, ends at 10:43. Another one starts at 12, ends at 2 o'clock at 14:18. So 2 hours. It takes 2 hours 18 minutes. So on the network analysis toolbar, we can again use the solve button. Total cost, total travel time for each road will be calculated. Optimized route connecting the various locations will be shown. So for both route 1 and route 2. So this is how we can solve the VRP problem as well. So these are some of the references you can look at. So to conclude, hyperlocal delivery model is being increasingly adopted all over the world. This kind of delivery, though conducted by a lone agent, cannot be modeled through standard travel demand modeling process either for passenger or freight. This is primarily a distribution problem which needs to be solved to determine the final network loadings. So whenever we are doing a freight modeling, we cannot do those direct OD, using gravity model, this kind of distributions. We have to solve the routes or the tours using this kind of distribution problem, and then we can load that to the network. So while this kind of last mile delivery trips, tours or restocking tours were earlier ignored in urban transportation modeling process due to their low volume, currently these are of significant volume and cannot be ignored. So we need to gradually incorporate this kind of analysis to determine freight movement in an urban area. Thank you.